Okay, we have here today another integral from the MIT Integration Bee 2024, problem 17. We have the integral of the sum from k equals 0 to infinity of sine k pi over 2 x to the k dx. All right, now to get started with this, at first this is kind of intimidating having this sum here inside of the integral. Now the nice thing to notice here is with just this sign here, notice k is going to be an integer value, and so we have this like an integer multiple on pi over 2, like every 90 degrees. And so at multiples of 90 degrees, there's only three values for sine. It's going to be either 0, 1, or minus 1. So I think maybe the easiest way here is to just kind of start plugging in values with starting with our k equal to 0. So we're going to have our integral around this whole thing. So like first, when k is 0, we're going to have sine at 0. So that's just going to be 0 times x to the 0. So of course that's going to be 0. Then for the next value, when k equals 1, we're going to have sine at pi over 2. So that's just going to be 1 times x to the 1. And then when k is 2, we're going to have sine at pi, so that's just going to be 0 times x squared. And then when k is 3, sine at 3 pi over 2, this is actually going to be a minus 1, and this is going to become x cubed. And this pattern is just going to continue on and on like this forever to infinity. But then just to clean this up a little bit, just notice for all the even exponents on x, they're all of 0 coefficients, so all those terms are going away. And so we can just kind of rewrite this something like x minus x cubed plus x to the fifth, all having odd exponents, just with this kind of pattern here. And then having it written out like this, we can kind of start to see a pattern where just to go from x to minus x cubed, well, we just multiply by minus x squared there. And then to go from minus x cubed to x to the fifth, again, we multiply by minus x squared. And so this is going to be true for all of these. And so this is actually a geometric series. Now we have our geometric series formula over here to the right. And now for this, our a value is just going to be our first term. So we have our a equal to x. And for our ratio, our r value, that's just going to be this minus x squared value. Now, one thing we need to do before we can use this formula, though, is we have this condition over here to the right that just says the absolute value of this ratio has to be less than 1. Now, what's different about this problem from other ones we've done is they're almost always definite integrals, and here we have no bounds. This is an indefinite integral. So with no bounds, we have no idea what x is, and so in a way, it's like we have no idea if this ratio meets this criteria, right? We've got nothing to go on. So in a case like this, the only thing I can think to do is go back to the original problem, that if x is greater than or equal to 1, then the whole integral is going to diverge. So really, in order to do this, I think what we have to do is we have to assume that the absolute value of x is going to be less than 1. And then for this is going to be true because then our minus x squared, this also is going to be less than 1 if this first condition is true. So making that assumption right there, I'm going to call this minus x squared our r value and just go right to the formula. So what's going to happen is this is going to become x over 1 minus our ratio minus x squared. But again, this whole geometric series is inside of an integral. So actually, let me clean it up before we integrate it. So this is just going to be x plus 1 over x squared dx. So let's just do this integral here real quick and we'll finish it off. Okay, now we have this all reduced to a very simple integral. I'm just going to do a quick u substitution for the denominator, take our du value, and we get 2x dx. I can create this 2x here, but I'll multiply by a half out front. We'll just go ahead with this real quick. This is going to become half du over u. Integrating this, we're going to get just half natural log absolute value of u, just back substitute, and then we're going to have our final solution of 1/2 natural log x squared plus 1. This is always positive, so I'll drop the absolute value plus c, and that's it. Okay, there you have it. Good one from MIT 2024. Thanks everyone for watching. Have a good day.